Hi, I'm Aaron Auerbach, and this is my 489Y final movie. In this class, we learned about remote sensing and applied our knowledge to create our own LiDAR device to scan campus. What Dr. Mitchell wants to do is to create an entire LiDAR scanned map of the entire campus, and we picked individual places around campus to scan so he can eventually have what would become an interactive map and what could be used in self-driving cars of the future. Remote sensing is using a sensor to image a distant target. So there's a difference between active and passive remote sensing. This device, as you see here, is an example of active remote sensing. There's a transmitter, which is in this case the line laser, as you see, and a camera that's up above that receives the data that is reflected by the target. So in my device, the camera is connected to the chassis using duct tape and rubber bands and is connected to a Raspberry Pi. Underneath the Pi will sit my phone that will be held by two rubber bands, and that is what I use to measure the angles of which I'm scanning. Underneath is an Arduino which I use to power the line laser itself. Right underneath the Arduino is a holder that keeps everything stable and connected to the tripod. And the final thing is the battery pack to power the Arduino. Before I could do scanning, I had to do a lot of setup. The first thing I had to do is make sure my Pi was ready to actually do the scanning. One of the things I had to do was download OpenCV onto the Pi, which took upwards of 4 hours to download. That wasn't it, I also had to download other programs onto my laptop and onto the Pi, including VNC Viewer, so I could access it from a distance. Another thing we had to do was to make sure that our camera was working well and calibrated properly. We compared it to a point laser. The point laser was situated a foot away, like in the chassis, and we took measurements at every half a foot to create a calibration curve. The idea of this was to make sure that the camera would be working fine and we can adjust our new data accordingly. As you can see, the values I got matched the theoretical curve pretty well. Oh, looky there, Nathan, the majestic grill, located just outside of Common 6. The reason we're studying this today is because of how close it is to modern life. It is so close to this living establishment, and it is relatively far away from its natural enemy, light. There are some windows that could give us some trouble during our nighttime spying. But otherwise, we hope to get a very, very good idea of what it does at night. And here we are getting a closer look at this majestic beast. We had to cover it with flour to keep it down and maintained, or else we wouldn't be able to see the laser. Right here is our scanning device, the LiDAR itself. The Arduino is connected to the battery pack to keep the line laser going, and the laptop is running VNC Viewer to make sure that this can all be seen. Now, one of the biggest problems that we did not anticipate was how the darkness of the grill itself would completely dissolve the laser. It's almost impossible to see in this light. Another problem was situating ourselves. We had to request a chair from a buddy to make sure that we could comfortably and safely scan. As you can see, there's our angle measurement, as promised before. A phone, rubber banded to the back side, and a lever to help change the angles. Right beneath the grill is a very reflective surface, which does a lot of damage in post-processing. And all around us, light. Light that happens to drown out the laser at every possible moment. Now that scanning is done, it's time to make the point cloud. First, All the files that were taken on the Raspberry Pi are taken off and put onto my laptop via CyberDock. After that, I turn to the Color Picker 2 program to check the HSV values, make sure that I am actually reading the laser line in each image. So what I have to do is alter that line of code right there to make sure that I'm actually reading the exact image I want to, which in this case, I'm going to take from the front and I'm going to read image 6. Now as you can see, it shows 3 images: a thresholded image, the original one, and track bars of the HSV values. As what I'm doing is I'm shifting the values of hue, saturation, and value to see if I can get the laser line to show up, which you can faintly see at the very bottom of the picture right there. Now that I have found my values for H, S, and V, I'm ready for the next step. I go into datageneration.py, make sure that I am working on the direct file that I actually want to work in. In this instance, I'm going to work in alignment images back to make sure I'm running all the pictures that I took of the back of the grill. And what I'm going to do is I'm going to print out a page called textresults.txt, one to each corresponding folder. So the next thing is to specify color lower and color upper. That's where the HSV values come into play. As you can see, it was not very easy. 3/4 of my sides did not have very clear or well-cut HSV values. The right, the left, and the front all had different values for each image. What I did was I started with an if statement. In this instance, if angle equals a certain value, the HSV is this value, in this case color lower. Whenever it wasn't, I would use else if to make adjustments. After fixing those values, I would run the code and save the .txt file, which you will see in the MATLAB next. I turn to MATLAB to patch the files together and remove any unnecessary noise. As you can see here, I inputted 4 different documents, and this is how I removed the noise of four statements and if statements. If the values were above or below certain extraneous points, then I just simply removed them and labeled them as 0, 0, 0. This I had to do for each and every side labeled A, B, C, and D. For each one, I also had to do some minor transposes, either flipping the X and Y axis or making sure that they were moved accordingly, adding or subtracting certain dimensions based on using the first figure. So as you can see, A, B, C, and D drew from the text files that I talked about earlier. Right now, the point cloud is loading because I have put a lot of values into MATLAB and it is trying its hardest. As you can see here, what somewhat resembles a grill. Each side is represented by a different color: green, yellow, blue, and cyan. It is not the greatest, but it does show some of the decent sloping up features and the sides relatively well. All that's left to do is to create a mesh from the point cloud. I go to Mesh Mixer and open up the .txt file that's created by the MATLAB image. In this instance, I have to make sure that the separator is what I used in MATLAB. To actually see what I'm doing, I make the points a little bigger and I eliminate any extraneous points that weren't caught by the noise filters I used in MATLAB. As you can see, this specific image is quite noisy, so there's still a lot of extraneous points that just narrowly escaped the grasps of MATLAB. What I have to do next is show myself the normals and compute said normals. Now, normally when computing normal, it uses a neighbor number of 10, but in my instance, I needed to use 10,000. What you want is all those blue lines to face in the same direction as you can see below. Next, I had to find the Poisson surface, which is not where it usually is. It is right at the bottom. And as you can see here is my mesh attempt at the grill. The point cloud turned out a lot better than the mesh. Thanks for watching. I would like to give a special thank you to Nate Mengers for helping me throughout this project.